This is Mihai Banu, founder and CTO of Blue Danube Systems. Today, I will be covering an introduction to Coherent Massive MIMO, boosting performance of 4G and 5G networks with software configurable low-cost phased arrays. Welcome to our series of presentations on RF Coherent Massive MIMO. In this introduction, we review the technology fundamentals and overall benefits of applying RF coherency to Massive MIMO. The other presentations in this series give technical details. Our RF coherent massive MIMO concept defines a new paradigm for massive MIMO, which has been made possible by a Blue Danube breakthrough in manufacturing super low-cost phased arrays. Given this breakthrough, we are strongly advocating the use of phased arrays in all massive MIMO systems because RF coherency can fundamentally improve the system performance, especially in real-world operating conditions. This is quite relevant in practice because conventional massive MIMO systems, which normally are not designed with RF coherency, suffer significant performance degradation in the real-world deployments. In our opinion, this new paradigm defines the next generation of massive MIMO technology for 4G, 5G, and beyond. Throughout the presentations in this series, we focus on sub-6 GHz systems, but the concepts and the techniques discussed are also valid for millimeter wave systems. Exclusive low-cost phased arrays in LTE operation. For many decades, phased array technology has been very successful in radar and space applications, but also notoriously expensive. At Blue Danube, we have invented and developed a new super low-cost phased array technology we call High Definition Active Antenna System, or HDAS. In October 2016, we used this phased array technology to demonstrate for the first time an FDD massive MIMO radio operating in live LTE traffic. This was also the first coherent massive MIMO system and produced significant cell capacity gains. Since 2016, we have deployed other units in LTE trials and commercial service, including service in cluster configurations, and we have demonstrated best-in-class capacity gains and other network performance enhancements. The respective Blue Danube product family is called Beamcraft. For the rest of this presentation, we will point out the fundamental reasons why coherent massive MIMO is producing excellent results in real-world deployments, and it is superior to conventional massive MIMO. The latter does not use RF coherency, relying solely on channel sounding and digital signal processing. A clear distinction between RF coherency and time alignment requirements for conventional massive MIMO will become clear shortly. RF coherency is much more stringent hardware design requirement, but once available, it offers a significant advantage for overall system performance. It is instructive to start with a quick review of the cellular technology. In the first cellular systems, a single antenna was used at the base station, or E-node B, and at the user equipment, or UE. This single input, single output, or SISO configuration allowed the transmission of only a single stream of data called layer, and no spectrum reuse within the cell was possible. Multiple input, multiple output, or MIMO technology supports spectrum reuse based on multiple antennas at both ends. In cellular applications, MIMO with 2 to 8 antennas at the base station and 2 to 4 antennas at UE achieves a few layers transmitted from E-node B to a single UE. This transmission method is called single-user MIMO, and it is a key feature for 4G LTE. The constant real-world demand for more and more capacity and the limited availability of spectrum have driven research efforts to find methods for more dramatic spectrum reuse. A popular concept believed to be a good solution to this problem is massive MIMO. By increasing the number of E-node B antennas to 32, 64, or even to a larger number, massive MIMO is theoretically capable of producing many more layers than regular MIMO and of transmitting these layers to many users. This operation is called multi-user MIMO, a greatly desirable effect for spectrum reuse. Multi-user MIMO by DSP-based 3D beamforming. In the literature, it is very common to describe the operation of a massive MIMO system as 3D beamforming. This terminology can produce confusion to the uninitiated because it refers to a very specific digital signal processing technique aiming primarily at interference cancellation, not at the creation of physical beams. This is illustrated by the heat maps shown on this slide. The color codes from blue to red correspond to signal intensities from weak to strong. Each picture is a two-dimensional heat map of the corresponding RF energy projected on a screen in front of the massive MIMO system. As one can see, the DSP-based beamforming creates energy heat maps for individual layers with precisely set peaks and valleys to avoid layer-to-layer interference. The strongest peaks in red do resemble localized physical beams, hence the justification of the beamforming terminology. However, the rest of the heat maps contain significant energy outside the strongest peaks. The resulting total energy transmitted by all layers is this complicated pattern, which loses any resemblance to four physical beams superimposed. Common sense tells us that the best connectivity between two communication points is by a wire, and the wireless connectivity closest to a wire is a narrow physical beam. In order to avoid confusion with DSP-based beamforming, we will call the result of physical beamforming a true 3D beam. 3D refers to the fact these physical beams can propagate in all directions of the three-dimensional space. True 3D beams, also known as pencil beams, have most of their RF energy within a cone, producing minimal interference to others outside this cone. Clearly, this is optimal for spectrum reuse. The 3GPP 5G standard has adopted extensive use of true 3D beams. If true 3D beams are used for multi-user MIMO rather than the DSP-based beams, the corresponding heat maps for four layers are shown here. Notice that even in the total energy picture on the right, we can clearly recognize four well-defined superimposed physical beams. To recap, not all beamforming methods are created equal, and this picture clearly shows why 3GPP has adopted true 3D beams. There are two main methods for generating true 3D beams. Dish antennas do so by physical construction and geometry. They are a good match for fixed beam or slowly moving beam applications. Dish antennas are low cost, but they are rather limited in capabilities as they can usually generate a single beam. They are not agile and not software programmable. The second main method for generating true 3D beams is by phased arrays. These systems contain a large number of active antenna elements which are RF coherent, that is, are matched in RF phase and magnitude with a very high degree of precision. When RF coherency is present, true 3D beams are created naturally and can be steered with very high speed without any mechanical movement, but only through proper phase changes of the individual antenna elements. Phased arrays can generate multiple beams and are fully software programmable. Unfortunately, they have always been extremely expensive because RF coherency is a difficult condition to realize in practice. This has impeded their application to commercial wireless systems despite their great success in high-end costly applications. This paradigm has changed, however, as we already mentioned. Next, let us make a few additional observations about massive MIMO, which in its original form does not require RF coherency, although its structure looks like a phased array. The original massive MIMO concept proposed by Marcetta and Ashekmin in 2010 does not rely on RF coherency to create true 3D beams, but rather uses DSP-based beamforming. The concept is intended only for TDD wireless systems where channel reciprocity between the transmit and the receive paths applies. The wireless channel is sounded with pilots in the uplink, and interference cancellation between multiple layers is calculated and applied in the downlink. A popular interference cancellation algorithm is called zero forcing. The DSP-based beamforming with massive MIMO requires digitization of all antenna signals and a great deal of digital signal processing, resulting in a complex and expensive system. In addition, DSP-based beamforming is extremely challenging for FDD, which represents the vast majority of sub-6 GHz cellular spectrum. Even more importantly, this method is fundamentally sensitive to practical imperfections. While in ideal simulations or in laboratory settings with no interference and static UEs, the method performs well, the practical performance rapidly degrades with low signal-to-noise plus interference ratios, mobility, hardware impairments, large number of users, and cluster deployment. This is discussed in details in another presentation of this series. Naturally, one can ask the question if there is any hope for FDD massive MIMO. The answer is a resounding yes, but RF coherency is required in order to create true 3D beams. The Blue Danube field trial results mentioned earlier are definite proof. Finally, we should also notice that DSP-based beamforming is not the only option in TDD. If we have RF coherency, true 3D beamforming works in TDD just as well as in FDD. Here we have a head-to-head comparison between HDAS and conventional massive MIMO. As a genuine phased array, HDAT is a massive MIMO radio with RF coherency creating true 3D beams in FDD and TDD. The conventional ideal massive MIMO system, also known as digital massive MIMO, performs DSP-based beamforming in TDD and has been tested in research labs by several universities. These academic testbeds are not practical for commercial use due to very large size and cost. The actual conventional massive MIMO products that OEMs have developed and used in field trials are simplified versions of the digital massive MIMO, which are hybrid systems called digital subarray systems. In these systems, every radio chain is connected to several antennas. Since RF coherency is a central topic of our story, let us examine the role it plays in true 3D beamforming for an active array. Here we show customary heat maps with corresponding horizontal and vertical cuts of radiation patterns simulated for a 12x4 active array with half lambda horizontal spacing and 0.7 lambda vertical spacing. This is the exact size of the Blue Danube beamcraft units tested in live LTE traffic. On the top left, we have the ideal RF coherent case. That is, we have zero phase errors between the antennas in the array, producing a textbook true 3D beam which has a narrow main lobe at both sides and small side lobes. In all the other cases, we introduce random phase errors across the aperture such that the combined RMS phase errors for the respective array is progressively 5, 25, 75, and 150 degrees. Clearly, for 5 degrees or less RMS phase errors, the radiation pattern is only slightly changed from the ideal RF coherent case, but for larger phase errors, the radiation pattern degrades dramatically, eventually losing any resemblance to a true 3D beam. Typically, a classical phased array, including Blue Danube's HDAS, has 5 degrees RMS or less phase errors, and therefore practically it is RF coherent. It is instructive to point out that the 3GPP requirements for time alignment between elements in an active array are more than 10 times looser than this 5-degree RMS requirement for RF coherency. Therefore, conventional massive MIMO systems built to 3GPP specifications or even twice as good cannot generate true 3D beams and must use DSP-based beamforming instead with all its limitations. Let us review the advantages of introducing RF coherency in massive MIMO. A first set of important advantages comes from the capability to generate multiple predictable true 3D beams without channel sounding and digital signal processing. This avoids the fundamental flaws of digital massive MIMO, providing far less sensitivity to practical imperfections and excellent FDD operation. In addition, the generation of vertical beams for city high-rises is natural and easy, otherwise a challenge for digital massive MIMO. Using true 3D beams is also optimal for multi-user MIMO operation due to significant separation of user at RF before any signal processing. Finally, the use of true 3D beams enables a major hardware simplification, reducing significantly the cost, the weight, and the power dissipation. In most practical situations, this hardware simplification comes without any loss of performance, but on the contrary with a gain in performance. More about this on a different presentation of this series. Another important advantage of RF coherency is that the true 3D beams produced independently of the wireless channel conditions can be shaped and switched from the cloud as often and as rapidly as needed to minimize the intercell interference of an entire subnetwork. This is a fundamental advantage over the conventional massive MIMO systems, which suffer from payload contamination and hard to manage intercell interference in cluster deployments. Yet another advantage of RF coherency is related to the issue of sub-band beamforming in hybrid massive MIMO. A common belief is that a hybrid massive MIMO system cannot perform sub-band digital beamforming. Since coherent massive MIMO is a special case of hybrid massive MIMO, one may incorrectly infer that coherent massive MIMO cannot perform sub-band digital beamforming either. This cannot be further from the truth. If a hybrid massive MIMO with RF coherency produces multiple true 3D beams, sub-band digital beamforming is possible just as in the case of digital arrays. The only difference is that in this case, the sub-band beamforming is performed between the true 3D beams rather than between the sub-array signals. The net result is the same with far less complex hardware. More detailed explanations are given in a different presentation of this series. Evolution of MIMO systems for cellular. For the reasons we just discussed, coherent massive MIMO system built on a low-cost phased array platform such as HDAS is fundamentally superior to conventional non-RF coherent systems and represents the next step in the evolution of MIMO technology, as shown in this chart. Starting from left to right, we have in chronological order the common 4G LTE MIMO, the Marcetta Academic Digital Massive MIMO, the OEM Digital Sub-Array Massive MIMO, and the economical Coherent Massive MIMO built on a low-cost phased array platform. First, let us examine the 4 key MIMO parameters used here, and then we will return to this chart. The 4 key parameters are the number of passive antennas in the array, the resolution of the active array, the number of digitizers in the active array, and the number of data streams that may be transmitted in parallel, called layers in 3GPP. The number of passive antennas defines the array aperture. Usually these passive antennas are placed in a planar square configuration, but other configurations are possible such as cylindrical, conical, and so on. The aperture of the array is very important because it defines the narrowest possible 3D beam that can be generated by the array, irrespective of how the signals exciting the passive antennas are generated. So a digital, an analog, or a hybrid array of the same aperture are all capable of generating equally narrow beams. None is superior to the others in this respect. The resolution of the array is the number of subarrays that can be controlled independently in phase and magnitude. The higher the resolution, the better the system performance in terms of side lobe suppression. A digital, an analog, and a hybrid array of the same aperture generate the same narrow main lobe, but the system with higher resolution will have smaller side lobes for better separation of users. The term digitizer is used here as synonymous with radio or digital radio or radio chain. This is because data converter stages with associated analog filters, digital filters, high-speed digital interconnections, and other supporting circuits form the core and the expensive part of the MIMO radios. The number of layers impacts the system capacity. In general, the more layers the better, assuming each layer carries a high data rate. It is important to mention that in a wireless communication system, the maximum number of such high data rate layers, also known as the number of degrees of freedom, is a physical attribute of the communication environment and not something that can be generated by signal processing. Signal processing can only extract what is already there. Adding to this fundamental limitation, hardware impairments, channel estimation errors, and schedule difficulties, in most outdoor situations the maximum number of average layers is a lot smaller than the number of antennas used in massive MIMO. Going back to the MIMO system evolution chart, we can now explain it in detail. The standard 4G LTE MIMO has up to 8 radios antenna pairs. Most LTE systems deployed to date have 2 or 4 radio antenna pairs. These systems have low resolution, small number of digitizers, and a small number of layers, but they are economical and they are the workhorse of 4G LTE. The Marcetta Academic Digital Massive MIMO has a very large number of antennas, such as 128, and has the highest possible resolution because each antenna is connected to a separate radio. However, the system is very expensive because there are just as many digitizers as antenna elements. The main reason for this massive brute force scaling of the conventional MIMO system is to increase the number of layers. In specially designed laboratory experiments without mobility and without adjacent cell interference, at low RF power and within controlled operating temperature, 16 or more layers have been demonstrated. Currently, the digital massive MIMO system is far from the possibility of commercialization due to very high cost, very large size, and many other impractical aspects. The OEM digital subarray massive MIMO was developed with fewer digitizers compared to digital massive MIMO, targeting a more economical design, thus decreasing the array resolution accordingly. In digital subarray massive MIMO, each radio chain is connected to several antenna elements, hence the name subarray. This decreased array resolution, in combination with using realistic RF power and considering user mobility, have lowered the expected capacity performance of this system to 8 layers for TDD and 4 layers for FDD. In contrast to digital subarrays, economical coherent massive MIMO can be designed to have as many antennas elements and as high resolution as the digital massive MIMO. However, the number of digitizer and economical coherent massive MIMO can be reduced to be no more than the number of expected layers. This hardware simplification has major benefits in terms of cost and power dissipation. An example of such a design is Blue Danube's high-definition active antenna system. Another important fact is that while all other MIMO systems have static and fixed antenna mapping to digitizers, the Blue Danube's HDAS has dynamic array mapping. This is an important feature for optimal integration with standard processors running massive MIMO 3GPP protocols. Coherent massive MIMO upgrade roadmap. It is important to point out that an RF coherent massive MIMO active array such as the Blue Danube's HDAS can be integrated into the 4G and 5G networks as well as into the SON systems. For example, on the left side we show the RF coherent massive MIMO active array producing multiple true 3D beams in 4G. Typically, 4G BBUs have not implemented multi-user MIMO today. The connectivity to the standard 4G BBU is done with CPRI. In this case, each antenna port of the BBU is mapped to a true 3D beam or to a linear combination of multiple true 3D beams. A natural use case here is flexible sectorization with time of day beam reconfiguration from the cloud. Although very simple and easy to implement, this application is a significant improvement of the 4G networks when upgrading with RF coherent massive MIMO arrays. This is far better than using passive sectorization because A. It allows better RF planning in presence of clutter. B. The network becomes software adaptable to traffic conditions from the cloud. And C. The network can be also software reconfigured from the cloud in case of RAN equipment failures. In the center, we show the corresponding flexible sectorization application in 5G. Here, the RF coherent massive MIMO array is connected to a standard 5G BBU via one of the several possible virtualized RAN methods. The full migration from 4G to 5G is done only through software upgrades, assuming the radios of the RF coherent massive MIMO array are 5G compliant, as is the case of Blue Danube HDAS. On the right side, we show the most advanced use case of the RF coherent massive MIMO array supporting multi-user MIMO operation. In this case, a 4G or 5G BBU implements multi-user MIMO functionality and uses the true 3D beams generated by the RF coherent active array to obtain optimal multi-user MIMO performance. In both 4G and 5G cases, we could have a regular MIMO system with up to 8 antenna ports or a massive MIMO system with up to 64 antenna ports. The RF coherent massive MIMO active array can map all digital ports of a massive MIMO BBU to true 3D beams. A more detailed description of this mode is presented in a different presentation of this series. Like before, the migration to this most advanced massive MIMO system is done by just a software upgrade. We conclude this introductory presentation with the outline of the rest of the series consisting of several topics. A first topic is a review of the conventional massive MIMO concept and implementation, pointing out several fundamental flaws of this approach. A second topic is about how RF coherency avoids the fundamental flaws identified previously. A third topic shows that, contrary to some incorrect beliefs, a digital massive MIMO system cannot overcome the lack of RF coherency just by virtue of being digital. A fourth topic deals with the Blue Danube field results from trials and commercial deployments. Thank you for watching this introductory presentation on Coherent Massive MIMO. Please join us for the other presentations in this series as they become available.